We have now established the vector diagram for a plane wind scenario. You have to ensure that the velocity of the plane with respect to the ground has to necessarily be along the line joining the starting city A with the destination city B. This is a necessary condition in order to land at city B. And this velocity of the plane with respect to the ground will be the resultant velocity by vectorially adding the velocity of the plane with respect to the wind and the velocity of the wind. Let's look at this condition mathematically. Since for a plane it is always necessary to have the destination at point B, the drift along the y-axis has to be necessarily 0. If the drift along the y-axis is not 0, then you will not end up at city B, but you may drift either above or below B, and thus you would have some displacement along the y-axis. The displacement along the y-axis has to be 0 and would mean that the velocity along the y-axis would have to be 0, as we are assuming no acceleration. The net velocity along the y-axis can be obtained by adding the y component of Vp with respect to w to the y component of Vw, and since their addition will be 0, they will act in opposite directions and will have the same magnitude. We assume the angle the wind makes with the horizontal as alpha. The velocity along the y-axis is Vp with respect to w sine of theta minus Vw sine of alpha, and this has to equal to 0, where alpha is the angle Vw makes with the horizontal. So in problem solving, we can use this as a condition. We also assume that the plane does not accelerate in the x direction. The velocity of the plane in the x direction therefore is Vp with respect to w cos of theta plus Vw cos of alpha, which is the addition of the components of Vp with respect to w and Vw along the x-axis. And the x components of both Vp with respect to w and Vw are in the same direction, so we can add them up. Alpha is the angle the wind makes with the horizontal. So this is the magnitude of the velocity Vp. Now let's use this to find the time taken to move from A to B. Since there is no acceleration, the velocity that we computed in the previous step, Vx, is a uniform velocity. The time taken, therefore, to travel from A to B is the distance from A to B over Vx. So you can see that this is very similar to solving the riverboat problems, and it all boils down to getting the vector diagram right. In plane wind problems, the velocity perpendicular to the line joining the starting and destination cities will be 0. The time taken can be computed as the distance between the cities over the velocity of the plane with respect to the ground.